My name is Dr. Kyle Kotowick. I'm really glad to be here after a couple of years of not being able to do conferences. It was a big part of my life for a while, so I'm thrilled to be back into it. I'm really happy to see a pretty full audience, so hopefully we'll have a good time. So I'm here to talk to you today about the Boeing 737 MAX, and I think most people probably have heard about this. It was quite a thing in the media back in 2019, just before COVID became the big topic. And we're talking about how humans don't always necessarily mix well with the technology that they're using. So I'll start a bit about me. I did my undergrad in computer science, master's in electrical and computer engineering, and my PhD in aerospace engineering at MIT with a focus in human systems integration. So that's why that's why you can believe some of the things I'm saying about this. I started my own company after I graduated. In Victon Labs, we focus on consulting and prototyping for complex systems. I do some human factors work as well, again in consulting, and then some software and infrastructure development, particularly in cloud systems. And we're based in Ottawa, the capital city of Canada. That's where I live. Quite beautiful at times until it starts to look like it does outside right now for most of the winter. And I want to open by saying that what we're going to talk about are things to consider, right? I'm not going to give you prescriptive directions on what you should do or how you should build or how you should design it. We're going to talk about things to think about, right? And things that you need to consider when you're designing systems. So a bit about human factors engineering, kind of my specialty, and what it is. And when I say this, a lot of people say, oh, I know what that is. That's UX and UI, right? And yes, it does encompass those. Those are two important components of it, but it's a lot more than that. And I got to apologize in advance for my PowerPoint skills. I am a back-end designer. I am not a front-end designer. So forgive me there. Biomechanics, right? So how human bodies work and how they operate. Cognitive processing, how your mind processes information and deals with it. Sensory input, how your different senses collect and process information and send it to your brain. Ergonomics, so how human bodies fit into technology and how you build things so that they are comfortable and don't break. And then mental models, which is really how you make sure that what is happening in your user's mind represents what is happening in the system and that they match properly. And all of this together, along with a bunch of other fields, is human factors engineering. And I want to talk about life-critical systems. And I bring this up because I think probably a large portion of the audience here might be here because planes sound cool, and I want to hear about them and them crashing. But maybe not so aware of how does this actually relate to me and what I do in my work. And so life-critical systems, obviously anything that involves risk to human life or that keeps someone alive or could kill them. And I think a lot more people actually work on these systems than might realize it, perhaps without even knowing about it or without recognizing that it is life-critical. Because we have aerospace, the hot topic of this talk, and clearly we have avionics and navigation and engines and all the mechanics of an aircraft are all life-critical because if they fail, then down it goes. But also, every other component you might not think about, right? The timer on the coffee pot in the galley is a life-critical system. It doesn't seem like it, but if that timer fails and the software in it fails or the hardware fails and the coffee boils over and goes down through the floorboards and shorts out some electronics, or if it burns a crew member that is essential for the safe operation of the aircraft, now it's a life-critical system. So there's a lot of things like that you might not consider, but they really are. We have emergency services, anything with police or fire or medical, clearly life-critical, not just the knowledge and training of the operators, but the technology itself that they're using. Telecommunications is a big one. If your cell phone fails, if the cell network fails, you can't call 911. In a lot of countries, elderly people rely on being able to call in their prescriptions to a pharmacy and have them delivered. Can't do that if your phone doesn't work. All sorts of things fail when communication fails. Automotive, right? Self-driving cars, very hot topic these days. A lot of people in here have probably worked on something related to that. Your algorithm fails and your car goes crashing into a wall at 100 kilometers an hour. That's not going to be great. Medical. So when I bring up medical, a lot of people immediately think of health devices, right? The things that are connected, ventilators and surgical robots and things along those lines. But more often, and I'm interested in this one because I actually spent some time working in the medical field, it's actually the software that the providers use for documentation that causes the problems. So imagine you have a piece of software where your intake nurse has to enter things like allergies and medications the patient takes, but it's an unintuitive piece of software. They don't like the way it's designed, so they just don't use it as intended. And then down the road, your physician looks at the patient's notes, sees that the allergy box is empty, and gives a medication. thinking that that'll be fine. Well, the patient has an allergy to that medication, they die, but it was never recorded properly because the documentation software had a problem. Lots of things outside of what you immediately think of as life critical. And of course, military, anyone who's working in an environment where they're trying to end lives is obviously life critical. And not only is the hardware and software itself intended for that purpose, but also it's being used in environments that are very austere and where it's being abused in ways that it shouldn't be, like smashed and through extreme heat temperature ranges and all sorts of issues that you have to think of. So it really covers a lot of different topics, and that's why I want you to think that this does actually apply to you as well. And I also want to mention that what we're talking about is not theoretical, right? These events happened, and a lot of people died from them. And while I have some jokes throughout the presentation to try to keep it fun and interesting, I just do ask that we keep in mind that a lot of families suffered from these and that it's a very important topic. And I also want to mention that we're not assigning blame here. I'm not an accident investigator, so I don't have that legal authority. And while it might sound like I'm blaming a company that starts with Bo and ends with ing, I'm not. So please keep that in mind if you're watching Boeing's lawyers. So let's talk about what actually happened. So we have two crashes, right? The first one, Lion Air Flight 610 in October of 2018, so just over 3 years ago. Crashed into the Java Sea near Indonesia at least 560 kilometers an hour. That was the last recorded speed that they were able to get from the flight recorder from radar, but it probably was much faster than that by the time it struck, and that killed all 189 passengers and crew on board. And then Ethiopian Airlines Flight 302 in about 6 months later, and that crashed into terrain at over 900 kilometers an hour, killing all 157 aboard. Now, the impacts of this were massive, right? The 737 was grounded worldwide starting 3 days after the second crash. I'm not sure why it took them 3 days to do it, but 3 days later. 387 aircraft were grounded, which affected 59 different airlines, and 8,600 flights per week were canceled. And this aircraft was grounded for 20 months before it was recertified to fly. Now, up until COVID, this was the largest thing that had ever impacted the airline industry, and major economic impacts throughout. The audit of the Federal Aviation Administration, the body in the United States that certifies aircraft as safe to fly, their process was clearly flawed, as we'll talk about later, and so they went under an audit from the government to see why their process was flawed, so that caused some strife. And then we have uncertainty in other regulatory bodies around the world. So up until this point, different countries, their airline authorities, aviation safety authorities had said, okay, the Boeing aircraft is built in the US, the FAA, we trust them, they certify it, so we're going to let it fly in our airspace and trust that they've certified it appropriately. Well, clearly they didn't, so now what do all these other countries do? Does every country now have to certify every aircraft itself? That's a major overhead and time sink. And then looking at cost-wise, $20 billion in fines for Boeing alone, $60 billion in canceled aircraft orders, so $80 billion is a lot of money to a company even like Boeing. That is a huge chunk of their revenue. At least $7 billion in cost to the airlines for the costs of those flights not being able to fly and having to maintain and store those aircraft for that long, and $100 million in lost income just for the pilots who weren't allowed to fly because the aircraft they're supposed to fly isn't allowed to fly. So big impacts, really had an effect around the world in the aviation industry. Let's talk about timeline. So the Boeing 737 is kind of a legendary aircraft, first released in 1967. So it's been around 54 years. It's ingrained into aviation history. So in 2006, Boeing says, okay, we've gone through 3 generations of this aircraft already. It's time to replace it. It's getting old. We need a new design. And so they plan what they call a clean sheet, meaning a clean piece of paper. You're starting from scratch design for the replacement. And then in December 2010, Airbus, which is Boeing's main competitor, launches the A320neo. Now, the A320 is an aircraft that is very similar to the 737 in terms of size and capability and passengers and range. So it's a direct competitor. It's in the same market space. And so Airbus launches the A320neo, and neo stands for new engine option. They took their existing airframe and they put newer, much more efficient engines on it. And this is very popular among the airlines. So the Neo sets a record of 730 aircraft sold at a single air show, and which is the most to date. And the month after, American Airlines orders 260 of these Neos. And the really important part here is that it breaks their exclusivity with Boeing. Up until this point, they had only operated Boeing aircraft. And now all of a sudden they're saying, we are willing to go through the logistics challenges, the maintenance and training programs and everything to take this new aircraft because it is just that appealing in the market. But they also say to Boeing, okay, we still like your 737, so we want some more, but we need them to have newer and more efficient engines so they can match the A320neo. And this really freaks out Boeing, right? Because they're about to lose one of their largest customers. You know, they're breaking their exclusivity, they're not selling at trade shows, and they're really worried about losing market share here. So they say, okay, we need to build this version of a 737 with these new engines for American Airlines anyways. Why don't we just make that our new product? And so they abandon their idea of building a complete replacement, and they focus on upgrading the existing 737 to a fourth generation, which they called the MAX. And then in 2016, the A320neo has its first revenue flight with an airline, and in 2017, the 737 MAX does the same. And so Boeing pretty much accomplished their objective. They managed to get a new product out to market that competes with the 320neo and get it flying within roughly a year timeframe. Before I go on, I did see on the speakers list that one of the speakers here is actually an airline pilot. Is that person here? Up there, okay. So I'm curious afterwards to hear your thoughts. I'm sure there'll be some great questions in the Q&A about this. Okay, so why is this important? Why are we talking about engines? More efficient engines are larger, right? So they take more space because they're called high bypass engines. Here's an image of the original 737 engine. From 1967, 1.25 meters in diameter. You see it's pretty small. It fits nicely under the wing. Here is the third generation, from 1997, 1.83 meters, substantially larger, and you can see that it's kind of moved forward and up on the wing. And here's the 737 MAX, 2.26 meters, much larger. Now the question becomes, how do you fit an engine that is twice the diameter of the original engine on the same airframe? And well, you don't, is the answer. You can't really do it, but you can kind of fudge it around so that you can squeeze it in there somehow. So what they did, here's a schematic that shows a better view. This is the original. You can see the engines are directly under the wing. Here's a third generation. You see they moved the engines forward on the wing so they could raise them up in front of the wing. That helps with the ground clearance. And here's the MAX. You can see they really took that concept to the extreme. And if you look at the top-down view, those engines are so far forward, they're basically hanging off the front of the wing. And even after doing that, you still have a very small ground clearance of 43 centimeters. And from a side view, you can see the same thing, just gives a better impression of how far forward those engines on the bottom are mounted. So why is this a problem? Why does it matter? Well, the nacelles, the casings that hold the engines, are actually what we call lifting bodies. They generate lift when air moves past them. They're basically an extension of the wing in that extent. And what the problem is that when you have something that generates lift that's moved forward on the aircraft, now the front of your aircraft wants to go up. And this causes your aircraft to pitch up. And this is particularly a problem, or this issue presented itself primarily when the aircraft was at what we call high angle of attack. And the angle of attack is a word you're going to hear a lot, and it means the angle of the aircraft relative to the air that it is moving through. It is similar to pitch related, but not exactly the same because it also depends on the direction of the air. And so when the aircraft's at a high angle of attack, this issue becomes more pronounced, and so your aircraft pitches up, it causes lift at the front, makes it want to pitch up more, and you have this reinforcing loop that is not good. And the FAA says, no, this is not okay, you can't do this, you can't have an aircraft that wants to pitch up on its own without any pilot input. And Boeing's own test pilots say the same thing. They say, we've been flying this, it feels off, right? It's not handling the same as the old 737s, it feels unstable, and this is a problem. So Boeing tries a couple different things, and they try to modify some aerodynamics to handle this problem, but due to the age of the airframe and the fact they can't really change it that much without redesigning the whole thing, they can't do it. So they decide to try to fix this hardware problem in software. And we get what we call MCAS, the Maneuvering Characteristics Augmentation System. MCAS is an algorithm, it's a piece of software that sits and operates in the flight computer. And what it does, so here, there's a sensor on each side of the nose of the aircraft. This is the angle of attack sensor, and it measures the angle of the aircraft relative to the air that it's moving through, or the flow of air, I should say. And this sensor is connected to the flight computer where the MCAS algorithm is located. And the way it works is that this sensor determines when the angle of attack is too high, and when it does, it gives that information to MCAS, which computes that and says, okay, our angle of attack is too high, we need to activate this system to bring the nose down. And what it does is it rotates the horizontal stabilizer, which is this black line in the tail of the plane with the circular red arrow. It rotates it back. And that generates lift at the back of the aircraft, which brings the nose down and tries to keep it stable. And so we have this nice closed loop system. It checks it, makes a compensation, checks it again, and keeps going and makes sure the aircraft remains stable. And this is great. This deals with the problem of too much lift at the front of the aircraft, causing it to continuously pitch up. So let's put this on a pretty little systems diagram. We have our flight control computers, and there's two of them in a 737, but only one of them is connected at any given time. And each one has its own angle of attack sensor, which is only connected to the computer on that same side of the aircraft. And so the pilots can toggle between which flight computer and therefore which angle of attack sensor is active, but only one is active at a time. Remember, this is old legacy hardware we're dealing with here. MCAS is an algorithm that sits in this computer, and when it activates, what it does is it rotates that stabilizer, which causes the nose of the aircraft to go down. And we'll be modifying this diagram later, so we'll come back to this. I want to take a little break to talk about something called type ratings, because they're very important in what happened here. So a type is basically a category of aircraft that have similar characteristics, and a type rating is what allows a pilot to fly any of the aircraft within that type. And type ratings are hard to get. I mean, they take a lot of time and money. Your pilot has to go through many hours in ground school in a classroom. They have to do simulator training, they have to do an oral exam, they have to do a check ride, and it's a long and intensive process, and airlines don't like this. They don't want their pilots to have to do this if it's not necessary, not only because this equipment is very expensive, the simulators are many millions of dollars, but also because every hour that a pilot is doing this training for a new type rating is an hour that they're not flying for the airline, and therefore the airline isn't generating any revenue. So it's a very expensive process. So they try to avoid this at all costs if they can, which is why you'll find that airlines generally focus on a few different types and try to keep it restricted in the number that they have. And then we have what are called variants. So the Airbus A330 is a type, and within it are several different variants. So they're similar aircraft, they're slightly different sizes, slightly different characteristics, but for the most part they're the same. And the A320 is also a type with several different variants. And if we look at a picture of the cockpits here, so the A319 and the A321 are both variants within the A320 type, and we see why they're kind of treated the same way. The cockpits are almost identical. Similar displays, controls, everything, flight handling characteristics are all very similar. And so they basically treat it as, if you know one, you can do the other pretty easily. And so your training to move into a new variant, if you already have a type rating, is very quick. It's usually an hour or so on a tablet, and rarely any simulator training required to do so. So it's low cost, it's low time commitment, gives a lot of flexibility, so airlines love this feature. And what's important to note is that the A320neo, this new aircraft that made Boeing so worried about market share, was given the same type rating as the old A320s, which meant that all the airlines that had these old 320s, all of their pilots could immediately fly the A320neo with minimal training. This is a huge factor in making it competitive in the market. Now the 737, also a type, and all the three previous generations of it were that same type. And so Boeing says, okay, well, nuts. If Airbus was able to do this with the A320neo, we're not going to be able to compete unless we do the same thing, so our new 737 MAX has to be in the same type as a variant. But the problem with this is that MCAS is a new control system. And a new control system means it requires different training, and different training means it has a different type rating, or gets assigned a different type rating. And a different type rating means it's no longer competitive, and this makes Boeing extremely sad, because they cannot compete in the market, and they will lose all of their market share to Airbus. So Boeing comes up with a solution, a great solution. They say, well, the problem is, it's MCAS that requires the training, so what we're going to do is we're just not going to tell anyone about MCAS. Because if you don't know about MCAS, you obviously don't need to be trained on it. And if you don't need training, you get the same type rating as the older models, and if it's the same type rating, then you now have a competitive aircraft again, and this makes Boeing extremely happy. Because now they've achieved their goals, they've gotten something to market pretty quickly that is competitive with the A320neo, and there are no major roadblocks, all the boxes are checked, we're good to go. And this is something that Boeing recognized. So, sorry, before I go on, I want to mention that you're going to see a bunch of quotes here throughout the rest of the presentation from a newspaper called the Seattle Times. As you may know, Boeing's major manufacturing facilities have historically been located around Seattle, Washington, in the US. And so the Seattle Times has a long and colorful history of covering Boeing aircraft and have done an excellent job of it for the most part. They actually won a Pulitzer Prize for their coverage of the previous generation of the 737. So that's why we use them as a reputable source. So Boeing decided that the pilots needed no extra training on the system, don't even need to know about it, not mentioned in the flight manuals, and that was done to earn a common type rating with the existing models so they could minimize the training of the pilots. Nice recap of what we just said. And Boeing recognizes this themselves. The CEO said, MCAS is fundamentally embedded in the handling qualities of the aircraft. It is not a separate system to be trained on, right? Because your pilot can't actually do anything directly with it, so why do they even need to bother learning about it? A little spoiler alert here, Mr. Muhlenberg is no longer the CEO of Boeing. And so the benefit here is that training on moving from the old 737 to the new one, little more than 1 hour training on an iPad, no simulator required, airlines love it, everyone's happy. So let's talk a bit about manual override, something that always comes up when we're talking about automated systems, particularly in software and hardware and how they play together. This is the cockpit of the 737 MAX, and a couple things to note here. So first we have trim switches. Now on the side of the yoke, the control column that the pilots use in a Boeing aircraft, is these little toggle switches, and you push them up in the plane trims so that it wants to go up, you push it down, it goes down, and it controls an electric motor which rotates the stabilizer on the tail. And then we have the stabilizer trim cutout switches. These are two little toggle switches at the bottom there, and if you turn these into the cutout position, if you flip them down, then it completely disables any electronic control of the stabilizer. So that motor will no longer function. And then we have the manual trim wheel. This is right next to the pilot's knees. And it is a wheel that is mechanically connected to the stabilizer. So there's actually cables going between the wheel and the stabilizer. So you can't disconnect it. And you can manually turn this wheel and rotate the stabilizer. And you'll see at the bottom there's a little hand crank that flips out. And that's how you would crank that wheel if you needed to. So let's add these components to our diagram. We have our trim switches up here. These send a signal to the flight control computers. They run that electric motor, which rotates the stabilizer. And our cutout switches is around here somewhere. It completely disconnects any electronic control of the stabilizer. And here we have our manual wheel, which is directly mechanically linked to the stabilizer, can't be disabled, always connected. So getting into the actual flights. First one, Lion Air. This is a chart showing the altitude and velocity of the aircraft. And hopefully people can see the problems with this graph. About 2 minutes in, we have a sudden drop in altitude, spike in speed. Pilots recover, gain some altitude, and then around 5 minutes in, for a 6-minute period, we have a series of drops and gains in altitude, and then finally a plunge into the ocean. And what's happening here is this MCAS system is kicking in. Gosh, I'm going to get into that in a minute. First, I just want to show you, this is what a plane looks like after it crashes into the ocean at that speed. There's very little left, and not only is it very difficult to find and deal with, but there's very little to recover, meaning that it's extremely hard to find the flight recorder or any other components that can help you with the accident investigation. So it's difficult to determine these events, and a lot of these events that we're talking about are based off of best estimates of what happened, but there's no guarantee that it's necessarily correct. So what happened, we suspect, is that this sensor, the angle of attack sensor that was connected to the flight control computer that was active at the time, was broken. And we think that it was broken when it was installed, or prior to being installed during the last maintenance cycle. And that sensor was feeding erroneous data into the MCAS algorithm. So MCAS was saying, oh no, okay, our angle of attack is too high, we must activate because this is what we were created for, and we will activate and rotate the stabilizer. And that rotates the stabilizer at the back and brings the nose of the aircraft down. And the pilots, they don't understand what's happening because they're not aware that this system even exists. So they try to use their electric trim to counteract this, right? They press that toggle switch, activates the electric motor, rotate the stabilizer, try to bring the nose back up. But MCAS is a very powerful system, and it activates for 10 seconds on, 5 seconds off, while it reevaluates 10 seconds on, 5 seconds off. And that's why you're really seeing this cycle, right? Because MCAS is kicking in, bringing it down, pilots are trying to recover, bringing it up, and we're going back and forth. But eventually, the pilots start to panic a bit and lose focus on what's going on. MCAS takes over and gets them into a dive that is unrecoverable, and they can't save it from there. And we go into the ocean. And So that's what we can see happening in this diagram here as well as a reminder. Right, we see those spikes in altitude, in velocity, and dips in altitude as this cycle happens. So after this crash, the FAA and Boeing get together and say, what could have happened? And I think at this point, internally, they're aware of the issue, but they still don't make it public. But they release what's called an airworthiness directive, which is basically a bulletin that goes out to every airline and pilot that operates this aircraft to tell them of something important about the aircraft. So they're required to read it and understand it. And their directive says that if this happens again, if in the event of runaway trim, you want to disengage the autopilot, control the pitch with the control column and the electric trim toggle switches. And if, after you've done that, relaxing the column causes the trim to keep moving, then set the stabilizer trim switches to cut out those two toggle switches I mentioned. And if the runaway continues, hold the stabilizer trim wheel against rotation and trim the plane manually. So they're just saying that in the event that this starts to trim down, right, try first disable the autopilot in case that's the issue. If it still happens, disable the automatic trim in case that's the issue. And if it still happens, try to control it manually. And then we come to Ethiopian Airlines flight, the second crash. And if we look at a graph of altitude here, we see it is very similar. Striking similarities, same issues. We see increases in altitude followed by drops and increases in drops. This one's kind of interesting because it shows a couple annotations of some events that occurred over that timeline. The low altitude warning telling the pilot to pull up, requesting to return to the airport for emergency landing, and then finally diving down into the ground. And so this one collided into terrain at, like I said earlier, over 900 kilometers an hour. This is what it looks like after a plane hits the ground at that speed. Again, it's a bit easier than a water recovery because at least the pieces are still there and not sunk below the ocean, but trying to find them and put them together is extremely difficult. There is very little remaining. So what happened on this one? Well, same issue. This time, they think it was a bird that struck the sensor during takeoff and broke the sensor. But it did the same thing. It sent a maxed out value and said, very high angle of attack, MCAS activates, nose of the plane goes down, same issue. But this time, those pilots have read that airworthiness directive. So they're aware that this can be a problem. They're aware of what they're supposed to do. So what they do, is they flip those cutout switches to deactivate the electric trim, and they try to use their manual wheel to rotate the stabilizer. But here's a problem. During takeoff, a pilot has the aircraft at full throttle. And it's one of the only times during regular flight that you're actually at full throttle. And what happened is, because this issue occurred shortly after takeoff, the pilots got distracted and forgot to throttle back the engines. And so this aircraft was flying at full throttle for quite a while and had reached a very high speed relative to where it was in the flight and the altitude. And what happens when you're moving very fast through the air and your control surface is already tilted back, as it is in this surface in this image, is that that's a lot of air moving against that surface, right? That's a lot of force pushing against it. And trying to counteract that force with a little wheel next to your knee is extremely difficult. And so these pilots, they simply couldn't do it. They could not apply enough strength to that to rotate that stabilizer. And so they recognized that, and they said, okay, the only way we're actually going to be able to move the stabilizer is to use the electric motor. But to do that, we have to re-enable those cutout switches and then use our little electric trim toggle switches again. Problem being that this whole time, MCAS was still running in the background. It just couldn't do anything because they disabled the linkage between them. But as soon as they re-enable it to try to use the trim switches, MCAS has an effect again, and it kicks back in and just drives them right down into the ground and into an unrecoverable dive. Now, to recap the events, Boeing modified an existing design, which changed the aerodynamics. They couldn't solve it without a redesign, so they solved it in software. They didn't tell the pilots or airlines about it, so they wouldn't have to be trained on it. Pilots don't know what's happening, and that gives us accident number one. They provide the airworthiness directive to tell the pilots that there could be an issue. They still don't say what the issue is or what this algorithm is that's causing problems, but they say just be aware there could be a bug in the system. But the pilots are not physically able to follow the instructions due to other issues, and we have accident number two. So this covers the events, right? This is the story of what happened with these planes and why and how they crashed. And now we're going to take this and ask some questions about what does that mean for us as engineers and developers? What do we need to think about from this? What are our takeaways? And the first question I want to ask is, when do you teach users about the inner workings of a complex system? Not just aviation, but any complex, high-performance, or life-critical system. Obviously, the question here is, should those pilots have been told about MCAS right from the start? So to illustrate this issue, I want to use an example. Let's say we have a generic car, okay, a new model, but there's a factory defect, and with a low probability, there can be this issue where it just accelerates uncontrollably by itself. It just keeps driving and accelerating. And you have two different ways to deal with this. Deep inside the technical manual for this vehicle, you see option number 1, the correct option. And that says that you need to hold the accelerator pedal at its maximum point for 4 seconds while simultaneously pumping the brakes 3 times at 1-second intervals. You have to apply the emergency brake at 33% and hold it release it after 8 seconds. And then after releasing the accelerator, but before releasing the emergency brake, you have to activate the 4-way hazard flashers and apply the horn for 3.6 seconds. Ridiculous example, but if you've ever seen a pilot's checklist for certain issues that happen in flight, it gets pretty extreme. Now, the good thing is this is guaranteed to resolve your issue. 100% chance of success if you do it right. If you recognize the issue and you apply the procedure correctly, it will solve your problem. And then you have option 2, which is turn off your engine and attempt to maintain control of the vehicle while you apply the brakes. And there's an 85% chance of success. You might go off a cliff, but you'll probably be fine. Now, say we have 2 users, right? We have your average Joe, and he goes to the dealership and says, I want a new car. And the dealer says, this is a great car for you, but just so you know, has a small little bug. And what should that dealer tell Joe about how to deal with this bug if it comes up? The dealer has maybe 10 minutes to tell Joe about it, and then Joe's off on his way to drive this car for the next 10 years. Which option does the dealer tell Joe? Then we have Speedy Sally here. She's an F1 race car driver. And she spends her entire career training on these things, right? She spends 4 hours a day studying, preparing, practicing, the other 4 hours a day driving. And she's able to learn whatever you tell her if you give her enough time to memorize it and practice it. How do you assign these 2 different options to these users? And I would say that normally you'd do something like this, right? Joe, you're going to tell him about it, and then if this issue occurs 3 or 4 years down the road, there isn't a chance in hell that he's going to actually remember that procedure and how to apply it, and then actually be able to do it under stressful situation, right? Whereas Sally can probably do it because that's exactly what she's trained for the last 4 years. And so this kind of gives the idea of you don't necessarily want to train someone on what is the best option. You want to train them on what is the best for them in their system. For Joe, an 85% chance of success is great because he doesn't have to memorize anything. This is just the intuitive thing to do if your car starts accelerating like that. Whereas Sally, since she can memorize it and has the ability to do so, we give her the procedure that is guaranteed to save her life. And these kind of form 2 endpoints on what I call a performance versus knowledge curve. On the x-axis, we have performance or complexity, because those often go hand in hand. And on the y-axis, we have the knowledge required to operate and maintain a system. And sticking with our theme of transportation, let's plot some modes of transportation. We have walking, very low performance, low level of knowledge required to do it. Cycling's a bit higher, and then driving your car, you're getting into quite a bit of performance, but you actually have to train and memorize some things. You have to do your driver's tests and training and all that. And then we have our F1 car up at the top. And it's not just cars, there are aircraft fit the same model. You have your little Cessna down at the bottom, right? Your beginner airplane that anyone can learn to fly with a little bit of practice. And then you have your commercial airliner, a big step up in both performance and knowledge. And then you have your fighter jets up near the top where you spend most of your time training and just a little bit of time flying. And this applies not just to transportation, but all sorts of things. Let's consider a CPU, right? You have your stock 2.8 gigahertz quad-core CPU in your laptop that my grandmother can operate without a problem. And all she needs to know is if it fails, you turn it off and back on again, and it'll probably work. Versus your overclocked CPU, right? In order to do that, I need to understand how that works. I need to know the methods required to achieve that. I need to know how to maintain it. I need to know about thermal issues and how to resolve it if there's a problem. Much higher performance, but a much higher level of knowledge required to do it. We have our little kiddie skis. Strap them on and go down the bunny hill, not a big deal. Versus your powder skis, you got to know not only how to ski, but also your boots, how to do the bindings, how to tension them properly, and what to do if there's a problem. And then similarly, you have your MacBooks versus your Linux computers, where you have a much higher performance for a higher level of knowledge. And that, I get very different reactions to that joke based on whether it's a front-end developer conference or a kind of more server-side conference, so I wasn't sure how it would go. So we put these on our graph, and we see that the trend holds, right? And it's really consistent across most different things in life that you might build. Now, the question being, should the pilots have been told about MCAS? Coming back to that. I don't know. Because on one hand, yes, these are experts who are operating a complex system, who can train on it, they have the time to learn and memorize procedures, and they know how to deal with these types of issues, so maybe you should tell them. On the other hand, a commercial airliner is an extraordinarily complex piece of machinery that has so many different subsystems and components that could fail that there's no possible way for one person to be able to memorize all of it. So, should they have been told? Maybe. Well, let's look at what actually happened. Boeing concluded that there would be little risk in the event of an MCAS failure, in part because of an FAA-approved assumption that the pilot would respond to the issue in a mere 3 seconds. So they're saying it's okay if it fails, because the pilot will recognize it, disable it, take over manually, it will all be fine. But then they said, we're not going to inform the pilots about MCAS in the manuals, even though Boeing safety analysis expected the pilots to be the primary backstop in the event that the system went haywire. So they said, it's okay if it breaks. Pilots will take over. They'll fix it, but we're not going to tell the pilots about it. And again, I'm not citing blame with this, but I think we can see why this is a major issue in the design, not necessarily the design of the aircraft, but in the way that it was handled and presented to the pilots in terms of training and materials and knowledge. So our second question then is, how do you ensure that users know what is happening? In this case, we assume that we tell the pilots about MCAS, they're aware of it, they know it's a system that can break. If it does break or has a failure, how do we make sure that the pilot is aware of that? And this brings us to something in human factors called mode confusion, which is a very hot topic. It applies to any complex system where a human's operating it, particularly an aircraft. And it's been cited as a factor in, I would say, probably the majority of aircraft crashes in the last 50 years. So it's a very important topic. Now, in an aircraft, you have a lot of different modes that an aircraft can be operating in. You have an autopilot mode and you have an auto throttle mode, and those are not necessarily the same thing. You have a takeoff configuration, you have a landing configuration, and you have a dozen different modes and configurations that the aircraft can be operating in. And in these different modes, sometimes the same controls, the same switches, the same displays do different things depending on what mode it's in. So if you're not fully aware of what the system is doing at any given time, you might not know why it's happening or how to deal with it. And this is before you even consider things like MCAS dancing around in the background, messing with your control inputs without telling you. And so what happens is your pilot can get very confused, right? They can say, or they can not know, why is the plane doing this? Or not know, how do I stop the plane from doing this? Because they're not aware of what the plane is thinking, for lack of better terms. And now I want to show a couple of videos that kind of highlight this issue. It's a combination of mode confusion and sensory input overload, we call it, where you get so much information thrown at you that you don't necessarily know what to do with it or you can't process it. So these are from simulators. This first one is actually from an Air France crash, Airbus A330, I believe, in 2009. They did a simulation of the crash. For people sitting directly in front of the speakers, I recommend cover your ears for a sec.
That's the alarm. Stall alarm. Over the next 4.5 minutes, the stall warning will sound 75 times.
It's supposed to be a bit louder. You might have turned it down a bit. And then so that's not directly related to the Boeing one, but it gives you an idea of how aggressive the alarm can be. Here's another one. This is from a 747 simulator.
Too low terrain. Too low terrain.
This thing's got long wings now. We can't.
Too low terrain. Too low terrain.
We're 500
Too low.
So this gives you an idea of how difficult it is to operate in this kind of situation. These pilots can barely communicate with each other, let alone focus on what they're supposed to do. There's an immense amount of information being thrown at them, and there's a huge field of research on this about how to avoid this issue, how to design your alarms and alerts and prioritize them and make sure they communicate the right information. In this video, there are 2 alarms going off. It's expected that in the 737 crashes, 4 or 5 different alarms would have been going off at a time just before they hit the water. So obviously very difficult to focus in those situations and really hard to tell what your plane is doing, what your system is doing, and why it's doing it and how to fix it. And just to summarize that, during the 2 fatal crashes that killed 346 people, the pilots struggled to understand all of the warnings that were being thrown at them in the cockpit. What we have to remember about this is not a new idea, right? This is not an unknown. This is not a surprise to Boeing or FAA or anyone else. There's an extensive field of research over 40, 50, 60 years. It really started kicking in during the Apollo program was when it became a huge field. And the FAA knew this, right? Based on lessons learned from past airline accidents, previous crashes, the FAA regulations stipulate precise design details for the warning displays that are aimed at making sure the pilots know what is going on, that it catches their attention, and that it averts any possible confusion. Now, number 2 here, catching someone's attention is very easy to do, right? You make a loud alarm and it will catch your attention. But doing number 1 and 3 in combination with number 2 becomes quite difficult, because when you try to communicate some detailed information to someone, the best way to do that is not a loud and aggressive alarm that startles them. So there's conflict here, right? And these regulations they're written in blood. Like, these are from crashes where people died is why they came up with these rules. And yet, in 2014, Boeing convinced the FAA to relax the safety standards for the 737 MAX related to the alerts that would warn the cockpit if something went wrong, warn the pilots if something went wrong during the flight. Boeing's reason for asking for this exemption was that the 737 design is too old and it would cost way too much money to bring it up to modern standards, and therefore we shouldn't have to do it. Now think about that for a sec, right? If you say that someone gives you a task and you say, I'm not going to meet your specifications because the system's too old, so I'm just not going to do it, and ignore them, especially in a life-critical system. I think the issue here is pretty obvious about why that's a problem in the design. Manual override. This one's interesting because we know that there was a manual override option in the planes for the stabilizer, right? They have that manual wheel that they can turn, and they have the cutoff switches that disable the automation. So how does this apply to other systems, right? As we're designing automated systems, how do we decide whether or not there should be manual override, whether our user should have any input whatsoever? So we have what are called levels of automation, and there are many different published scales for this that go anywhere from 4 to 12 different levels of automation, but I've kind of summarized them into a simpler version here. So 4 levels, your first level being providing helpful information, a system that tells you something that helps you with your task, right? So think GPS on your phone or a navigation system in your car. It helps you do what you're trying to do, but it doesn't actually control anything. Then we have automatic control when directed by a human. So this is more like your cruise control, right? It turns on when you turn it on, it automates until you turn it off, and that's all there is to it. It doesn't do anything on its own unless you tell it to. Level 3, you have automatic control unless directed by a human. It's more like your Windows Update, right? If you don't do anything to intervene, it will update, it will restart your computer, and off it goes on its own unless you intervene to stop it. And then level 4 is your automatic control with no human override. And this one's kind of hard to think of an example for because there are relatively few systems in the world where there isn't some sort of big red emergency stop button to shut it down. But you see this more in super complex technical pieces of equipment or things where there's very high latency, like spacecraft. I'm not sure if you remember the New Horizons going by Pluto and taking those photos. That entire procedure was choreographed and automated, and there was no way that a human could stop it once that program was sent. So that's kind of an example of how that works there. So where does MCAS fit in this? Right, obviously, it's not level 2 because it occurs without a human doing anything. Is it level 3 or 4? Well, there is a manual override, so we'd say 3, but you cannot enable your manual override without also disabling a lot of other important systems. In this case, they could not disable MCAS without also disabling the electric trim motor that they would need to rotate the stabilizer back into position. So is it really a manual override if it breaks a bunch of other things in your system? I don't know. I'd say it probably is not. And so these are things that, I'm not saying you should or should not choose one of these levels of automation for your systems you're designing. I'm saying this is something you choose in advance going in with very careful planning, because you don't want to be dealing with these issues down the road after you've designed your system and you start inserting things that fall in different levels of automation here and mess with your safety analysis. And which one you choose really depends on a lot of different factors, from who your users are, what level of training they get, what type of system you're using, and most importantly, what the consequences are if your automation fails and you either can't intervene to stop it or you can't intervene and do something more effective. So a system that, if it fails, doesn't hurt anyone, it's much more okay to have a fully automated system than something that's like an aircraft that will crash if it doesn't. So let's talk about redundancy. Now, this is further away from human factors and human involvement at all, but we've spent all this time talking about the planes and their designs, so it's good to touch on. Hopefully, in our diagram, most people can see the flaw in terms of redundancy. The two flight control computers are redundant, and they're there for that exact reason, and I believe they're actually built with different components, different architectures, different software by different manufacturers to make sure that if there's a bug in one, then hopefully it won't be replicated in the other, and you could switch from one to the other to resolve the issue. But each one is only connected to one sensor, and if that sensor fails, the computer does not realize that and therefore has no way to know that it should switch to the backup computer. It can only be done manually. This is a diagram showing the readings from the two sensors on that aircraft, the two angle of attack sensors during the crash. The issue is pretty obvious. The sensor on the left broke early on and maxed out its readings. The sensor on the right was working fine, but the sensor on the left was the one that was connected to the active flight computer and therefore the one that the aircraft was using for its control inputs. So talking about redundancy, what does that mean? Well, first off, please don't ever let a critical system have a single point of failure. Right? Anyone in here who does DevOps, infrastructure, high availability work like that, hopefully already thinking about that and incorporating that into your practices, thinking about multi-regional architectures, active-active failovers, etc. Very important part when you're talking about life-critical systems in particular. Second, don't let one broken sensor affect good sensors. Because what happens if the two sensors disagree? In the graph I just showed you, some systems might say, okay, we're going to average our two sensors and we'll probably get an accurate reading. Well, in this case, clearly that wouldn't have worked either, so it would have been very erroneous data. So what do? Ideally, you add another sensor to do some sort of voting mechanism. This is how a lot of distributed systems work that you might be familiar with. I think Apache Zookeeper uses a similar system to this to make decisions. And you can try to eliminate the one that disagrees with the other two, and hopefully at least 2 out of 3 will be valid. Alternatively, another approach is to force a manual override. So if you can detect that your sensor is giving you erroneous data, then maybe you can say, all right, I can't trust this data. I don't know what I'm supposed to do, so I'm just going to deactivate the automation and let the pilot take over, the human operator of whatever system take over. But imagine you're flying your plane, and you're focusing on something else, like your checklists or your navigation, and all of a sudden your autopilot deactivates for this reason or any other reason, doesn't notify you, and your plane just starts drifting off to the side, and you have no idea why it did that, why it deactivated, what the problem is. And now you get into mode confusion, which we talked about earlier. And so you see that these issues are often connected in this web of messy problems that are very difficult to solve when you're trying to design. And again, I don't have an easy answer for you on how to do it. Adding more sensors for voting costs more money. There's more parts that can break. Trying to average data doesn't work. There's no easy solution, but you have to think about what's going to be most relevant to your design during the design phase. And let's talk about change management. This is a big one. Again, not necessarily related to human factors. I guess if you're considering the developers as the humans, then yes, that is human factors, but not the pilots. So with MCAS specifically, this is an interesting one because the original version of MCAS was activated only if 2 distinct sensors indicated an extreme maneuver, so it required a high angle of attack and a high G-force in order to trigger the MCAS algorithm. In the initial design, it was designed as a backup in case the plane somehow got out of its flight envelope and was pitched up at a high angle of attack, and this problem started to reinforce itself, and this system was there as a safety measure to cover for that. But what happened is that during the flight testing, the test pilots said, wait, we love this. This is a great feature. This makes it feel more like the older 737s. It makes it feel more stable. Give us more MCAS. And so Boeing said, okay, we will do that. And they decided to extend the range of when that system would operate into the takeoff phase. Because during takeoff, you're naturally at a very high angle of attack because you're trying to get off the ground. And this problem is likely to be an issue where you have too much lift in the front of the aircraft. So they said, okay, we're going to use MCAS for takeoff, but the problem is that at takeoff, you're moving pretty slow, so there's no excessive G-force. So what they had to do is they had to remove the G-force sensor as a trigger because then it wouldn't, if they left it, it wouldn't have worked for takeoff. But that meant that MCAS is now activated by the single angle of attack sensor. So you've reduced it down to a single point of failure. The other problem is that this is a system that moves the control surfaces of the aircraft, the stabilizer, to apply aerodynamic forces. when you're moving at low speeds, you have to move a control surface more than you would at high speed in order to have the same force, right? Because it's a factor of the movement of the control surface times the airflow moving over it. So in order for the system to work during takeoff at low airspeeds, they had to expand the range of motion of MCAS and how powerful it was. So when the planes entered service, MCAS was capable of moving the tail 4 times further than it was stated in the initial safety analysis document. So they took a system that was designed to be a safety feature. They removed one of the triggers, so a single point of failure. They quadrupled the power that it had, and during this entire process, not once did they redo the safety analysis. So all of the FAA's decisions of what was okay about this was based off an analysis that was based off a design that was completely different than the final design. And this, I think, is a complete failure of change management, right? Because all of these changes should have been connected and triggered the new safety analysis, new reviews, to make sure that all these different implications are considered. And then finally, I want to talk about retiring a system. And I think anyone in here who's worked on like legacy systems, you know, like your 40-year-old code from the bank or something else that simply doesn't even exist anymore, and it's hard to find someone who even knows the technology, will recognize that there are points where you simply can't push something any further without it becoming very fragile or risky or having some other problem. Boeing had that thought, right? They knew that their 737 had already gone through 3 generations and it was time to build a new design. And that was what they were going to do. But due to market pressures and competition and the lack of oversight from the FAA, they were able to build a 4th generation of the 737 and really push that boundary further than it should have been pushed and built what was at the time an unsafe aircraft. And so I think this is important for us as engineers to really consider, you know, if we're asked to work on a system like that, you know, just patch that bug. Don't worry about the rest of it. It'll be fine, even though it's 50 years old. That's a risk, right? And that is something that we can't just accept blindly as something that'll be okay. And we really need to consider it when we're working on projects. And I want to close with a brief mention on what our responsibilities are in these types of environments. So realistically, you know, as if you're a freelancer particularly, but even working for a large company, you're never going to be in a position as a developer where you are responsible for seeing the overall picture and how these components interact with each other. You know, that is a job that there are specific roles for systems engineers, integration engineers who do exactly that to make sure it works. But that doesn't mean we're just off the hook entirely and can just follow specifications blindly to build something that slots into a module in a life-critical system and expect it'll be okay. And I think that it kind of falls to us to recognize when something might be a problem. You know, if someone says, please quadruple the power of this control system, and then just do it and not say, is this going to interact with anything else? Is this going to cause any problems? Is a little, well, something we... you need to consider and be okay with the idea of questioning that and asking the tough questions. Is this going to be safe? And if your employer discourages that or has a problem with that, then I recommend you find a new employer. Because what I guarantee you don't want is to be in the situation that a bunch of Boeing engineers are right now, where they regret a lot of decisions and have quite a weight on their conscience for the rest of their careers. So with that, I want to thank you for your time. And hopefully you enjoyed this presentation and the topics we covered. I know it's kind of a little depressing and morbid at times, but important stuff to consider, and hopefully some things for you to take forward into future positions. Thank you. Oh, my mic is off. Let's say I have 6 minutes. If anyone has any questions, I'm happy to answer. Also, you know, keep going. Don't worry about leaving. But if there are any questions, I'm happy to take them. Yes?
What happened to the plane now? Is it flying?
Yes, the plane is back in service. It was approved. The funny thing about it is I would say that the 737 MAX is now probably the safest aircraft in the sky, because it is the only aircraft that has gone through such extensive review of every component in it, because no one was going to let another problem slip through. So, yes, it is approved in flying. I actually flew on one coming here. Yeah. Any other questions? I can't see, sorry, the lights are there. But yes, there.
How come the test pilots didn't run into the same problems in the last version?
Sorry, how come the test pilots didn't
Run into the same problems?
Well, because these problems, so for the most part, they loved MCAS, as I mentioned, because it compensated for that problem with the aerodynamics. So the plane felt more stable when MCAS was doing its thing. But the problems occurred when the sensors broke, and the sensors breaking was not part of the test plan. So I think Boeing's initial safety analysis estimated this problem at like happening in 1 trillion flight hours or something like that. So it wasn't part of the test plan. And even then, the impact, they considered a major effect, which is actually a relatively low category below a hazardous and catastrophic effect. Yeah, their scale is a little wonky. But so even though, so it was a low probability and a low effect, so they said, we're not even going to bother testing these systems. Yeah. Yeah, if you have your hand up, just shout out because I can't see it with the lights. So.
Did Boeing change anything or just inform the pilots?
They changed the algorithm. I'm not sure exactly what they did on the hardware side. I know they modified the algorithm, and I believe they set it up to... so there's actually an interesting thing where that plane was sold with an optional package. It was not included in the base model, and if you notice, the two crashes were by kind of low-budget airlines, and they had purchased the lowest cost aircraft. And so they didn't purchase this optional package, which actually reads the data from the two sensors, the two angle of attack sensors, and compares them to, and gives an alert if there's a disagreement. It's called a disagree alert, and it shows a light saying these sensors, one of them is out of whack. So they did not include that in the base model. I believe one of the things they changed was they made that part of the standard package, along with some other changes. They changed the software, and I think they may have connected the two sensors so that they're both always connected to both computers, but I'd have to double check that one. Yeah. All right, well, thank you very much again, and if you see me later, feel free to strike up a conversation about this because I enjoy talking about it.